All right, we're at section 21.2. We're actually going to cover 21.2 and 21.3 in this video. 21.3 is very short, but we're talking about heat pumps and refrigerators. Now, if you look, let me minimize this. If you look, this looks very similar to a diagram we had previously, but if you look, the arrows are pointing in a different direction. Every one of these arrows is pointing in a different direction. The Q hot was going to the heat pump. The Q cold was going from the heat pump to the cold reservoir, and the work was going out of the what we called the heat engine. Now notice everything is reversed here. You're putting work. The heat pump is you're putting work into the heat pump, which pulls out the cold, the 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 Q cold. It pulls it out of the cold reservoir and puts it into the into the hot reservoir. So work is done on the heat pump, and so the energy Q cold is drawn from the cold reservoir, and it's expelled. The Q hot is expelled to the hot reservoir, and this is the basis for a refrigerator. You pull out whatever energy is in the refrigerator part, pull it out, and it gets even colder, and expel it to the outside air. So here's an impossible. Notice that. Well, let's read the paragraph. It is impossible to construct a cyclic machine whose sole effect is to transfer energy continuously by heat from one object to another object at a higher temperature without the input of energy by work. We learned in previous chapters that energy goes from a hotter item to a colder item. It's not spontaneously going to go from cold to hot. And that's the impossible situation they're showing here, that with no work, notice there's no green arrow, there's no work being put in. It's not going to arbitrarily pull cold temperature and transfer it to the hot. That's the impossibility part. So there's two different statements, and they're very similar. The Kevin Planck statement: it is impossible to construct a heat engine that, operating in a cycle, produces no effect other than the input of energy by heat from a reservoir and the performance of an equal amount of work. The Clausius statement says it is impossible to construct a cyclical machine whose sole effect is to transfer energy continuously by heat from one object to another object at a higher temperature without the input of energy by work. So you need input, you need work put into this heat pump in order to transfer the cold into the hot. And here we have a refrigerator, and you can see that the coils in the back of the refrigerator transfer energy by heat to the air. You have the compressor here, and the compressor compresses the refrigerant, and it expands. When it expands, it cools, and it draws the whatever energy is in the cold chamber, it draws it out so that it gets colder, and it expels it here at the back of the refrigerator. And the coefficient of performance, the COP in the cooling mode, is the energy transferred at low temperature divided by the work done on the heat pump. And the coefficient of performance in the heating mode is the energy transferred at high temperature, work done on the heat pump. So it's one is the absolute value of Q cold over the work, and the other is the absolute value of Q hot divided by the work. Okay, here let's look at a little quiz here. The energy entering an electric heater by electrical transmission can be converted to an internal energy with an efficiency of 100%. And so that's a factor of 1. By what factor does the cost of heating your home change when you replace your electric heating system with an electric heat pump that has a coefficient of performance of 4? Assume the motor running the heat pump is 100% efficient. So you have the COP of the first one is 1, and the COP of the second one is 4. So it's 0.25 0.25. So that's the factor by which the cost of heating your home goes down if you convert it to a electric heat pump that has a COP of 4. Okay, that actually ends the 21.2, but we're going to go on with 21.3, reversible and irreversible processes. And the first thing to know is that there are no such things as reversible processes. Every process is irreversible. You drop a cup, it shatters into pieces. The pieces aren't going to suddenly reassemble themselves. That's an irreversible process. You can get, oh, I lost my notes. Let's see. You can approach reversible process, although all real processes are irreversible. Some are almost reversible. If a real process occurs very slowly, such that the system is always very nearly in an equilibrium state, the process can be approximated as being reversible. So you can approximate it, but you'll never get to a truly reversible process. But we'll be talking about reversible processes anyway. Here's an example. You have a gas at some initial temperature, and you with a membrane, there's a vacuum above it, and when if you can puncture the membrane, the gas is going to leak out, and the volume is going to change. Now, no work has been done, so the work is zero, but you can, if you try to return it as a cyclic process, if you try to return it to its initial state, you have to do work on that little piston to get all that gas that has gone into the vacuum back down into the below the membrane. And so you have to put work. And so there's this is really a irreversible process. Even if the first process where you puncture the hole is an adiabatic free expansion of the gas, you can't, you have to put energy into it by compressing the piston to get it back to its original state. And you've probably heated up the insulating wall and things like that. So things have changed. There are no reversible processes. Okay, and that's going to end the section 21.2 and 21.3.